So in this lesson, we are going to learn several pretty important theorems related to polynomials and their graphs, and how we can use those graphs to solve polynomial equations. The first problem right here to start off our lesson is sort of a review of something I taught you last chapter back with quadratics. Except now, instead of looking at a nice parabola quadratic graph, we're looking at some sort of a polynomial. And I can tell that this graph is a polynomial because it has those kind of trademark bumps that we've talked about. And the arrows on the graph are both pointing downwards here. Polynomial graphs point down or they point up towards the ends of the graphs. And they ask us for this first problem to write the equation for this graph in factored form. Factored form, if you guys remember, is when you have your little parentheses set up. And we learned a really important rule related to the graph of quadratics, and that rule still applies to general polynomials. Remember that we learned way back when that the x-intercepts of a graph are the solutions to the equation if it's equal to 0. So the x-intercepts are the solutions. What that tells me is that I can look at where this graph hits on the x-axis. For example, that first point right there is x equals a -4. Well, if I know that -4 is a solution to this equation, that means that I must have the parenthesis x plus 4 in my equation. I know there needs to be an x plus 4 because if you solve this and equal it to 0, you're going to get a -4. Then I have a -3 right here. Well, that tells me that I must have the parenthesis x plus 3 in my equation. And then if you keep going with the same logic, I hit at 0 right there. So I could do x plus 0 or x minus 0 or even just x for one of my parentheses. And then finally right here, I have a +1. So if it's +1, I'm going to have x minus 1 for my equation. So when you look at a polynomial's roots, the x-intercepts, you can build the equation off of those roots by doing the opposites for each of your little parentheses right here. The only thing that this strategy, I guess there's two things that this strategy doesn't do for us. One is that it doesn't tell us what kind of number goes right here in the front of the equation. Like, is this a 2? Is this a 4? What number is going to get multiplied for my constant in the equation? We also have to consider whether it's positive or negative. So when we look at this problem right here, this graph has arrows that are pointing downwards on both sides. So I know that this graph is going to do something with a negative number. So what I'm going to have us do for this part right here, I'm honestly not super concerned about the exact number that goes here. If I wanted to know that, I would plug in some other coordinate and solve, like I've done with, we did problems like this with quadratics where we wrote a right here and then we solved it. I don't need you guys to worry about that. But what I care about is whether it's a negative or a positive number in the front. Since this graph is pointing downwards, you're going to put negative. Were it to be a situation where the graph was pointed upwards instead, you can put a positive in the front. So we're not going to concern ourselves over this number right here. We're just going to worry about whether it's negative or positive, okay? But this is a pretty good way to build your basic equation here. If I asked you to write it in standard form instead, all you would need to do is FOIL out these parentheses, okay? So that connection, if you know your x-intercepts on a polynomial, you can sort of build the equation in factored form. That's kind of a big deal. So let's progress, and what I want to do now is discuss how you make a detailed graph for a polynomial. Because we learned a lot of patterns and shortcuts and stuff like that, but how do you actually make a graph for a just random equation that's thrown your way? So I'm going to show you two ways to do this. First thing I'm going to do is show you how this works on your calculators. You may or may not have one of these handy when you're watching this video. So just kind of follow along with me, and then we'll talk about it. So the first thing I'm going to do is I'm going to go to my y equals menu up here, and then I'm just going to type in my equation. And when you're typing in your equation, we're going to go ahead and hit graph once it is typed in. So I have a plus 4x, and I have a minus 8. And once your equation is typed in, we're going to hit graph. Get used to whenever you graph something on these calculators to hit zoom and then standard, choice 6. It resets the window, which mine already was, but that way we're all looking at the same thing here. Now this looks pretty good, but I need to see just a tiny bit lower because this part of the picture got cut off a little bit. And remember the way that you do that? If I need to see lower on my picture, I'm going to go to the window. I'm going to leave everything the same here, but I'm going to make my Y minimum smaller so I can see a little further down. I'm going to try a -15 and see if that's good enough. I might have to go even lower. So it lowered it to a -15 right now. And actually that'll work out great. So when you graph a polynomial, you need to give me a couple of things. We gotta know the x-intercepts, or the roots, because those are the solutions that we've talked about. We also want to know where these bumps are on the picture. So I'm gonna start with the x-intercepts because we've done that before. Remember, you go second, calc, to the trace menu here, and the option for 0 finds your x-intercepts. So if I choose that, I need to go left bound would be somewhere on the left of this point right here. So I'm going to put my cursor like there. I'm going to hit enter. Right bound on the right side, which would be down here somewhere. You're basically sandwiching that x-intercept in between your clicks. And then guess, I'm going to go as close as I can, and I'm going to hit enter again. That tells me it's like -1.49. And I'm not sure why the calculator does this sometimes. 1e -12 means move the decimal 12 spots over. It's like 0.00001. Basically, this just rounds to 0. I don't know why the calculator doesn't just say 0 on this. So my first x-intercept is -1.49, comma 0, approximately. And I'm going to go ahead and write that down for myself. So when you graph one of these things, the first thing you're going to do, the roots are the x-intercepts. I just got -1.49, comma 0 for my first roots. So I'm going to go back here, find my calculator, and then I'm going to go and do the same thing for this other x-intercepts. So I'm going to choose 0 again and scroll my cursor. This time the left bound is going to be on the bottom of this points. So the left bound's like over there somewhere. The right bound is over here somewhere. And then guess my other x-intercept is about 3.58, comma 0. 3.58, comma 0. So I'm going to write that guy down. The other thing that I want you guys to have for me before you actually graph this thing, we need to know all of those bumps on the graph so we can make a good picture. So if I'm going to do that, I'm going to go to that same menu, second calc, but this time there are options for minimum and maximum that I'm going to use. So I'm going to go minimum first. My graph has 2 minimums right here and also right there. So you use the same process, and honestly, it might be easier because left and right is less confusing on these. Left bound for this guy would be like here, would be somewhere over here. So I do left bound, I do right bound, I guess, and it tells me my minimum is -0.60, -9.65. So you actually do need an x and a y for this. So -0.60, -9.65. So my minimums, relative minimums, I guess, I got -0.60, and it was like -9.65, I think. I think it was a -0.6. I can't remember. I'm going to look again when my picture comes back up. Yes, it was. So I'm going to go get my other minimum. And I know this is a little bit tedious doing all this, but it goes faster once you know how it works. So my other minimum is like over there. So my right bound, so that point is 2.63, -13.78. 2.63, -13.78, I think I said. And I have one final thing to find, and then I am done with my calculator here. So if I go and get the maximum, you go to that same menu. And then for my maximum, my left bound, I'm trying to get this point right here. So my left bound's like there, my right bound. And then it's going to tell me my maximum is 0.78, no, 0.79, -6. So 0.79 comma negative 6.00. Once you have all of this information in place, you're ready to make your picture. Okay, so I'm going to go ahead and I'm going to make myself a nice looking graph. Now, my x's on this problem are fine going by ones because all these x numbers are pretty small. But my y's, I do have to fit in a negative 13.7. So I'm going to make my y-axis go by 2's instead. And when you go by something else, make sure you label it. So my y goes by 2's, and then my x is going to go by 1's. So I'm just going to graph all of these points right here to make sure my picture, I see kids do this sometimes, and I'm okay with it as long as you say what's happening. So the y is going to be by 2's, and the x is going to go by 1's. So negative 1.49 would be like there. Positive 3.58 would be like here. Then I have to graph these guys, remembering that my y's go by 2. So a negative 0.6, negative 9. So that's negative 2, negative 4, negative 6, negative 8, negative 10. So negative 9.6 would be like there-ish. Then I got to do a 2.63, negative 13. So 2.6, negative 2, negative 4, negative 6, negative 8, negative 10, negative 12, negative 13 point something is going to be in that ballpark. And lastly, I have 0.79, comma, negative 6. 0.79, negative 2, negative 4, negative 6. So once you have all of those dots in place, these are actually the dots that you need to draw me a good picture. We saw the end behavior on this graph is that the arrows pointed up both sides, and that shouldn't be surprising because it's a positive graph and an even graph. So what you're going to do is start out going up, arrows pointing up, you're going to hit your dots right here like this. And we do the little bumps because it tells us where to turn around when we draw our graph. So mine's a tiny bit wobbly right there. But you can see once you do like a little connect the dots deal right here, that you get a pretty good picture. And that was pretty much what my calculator looked like right here. So you can see that this is the same picture. Now, real quick, I want to show you guys a second option for graphing that honestly is easier than using your calculator. Because some of you probably don't have a nice calculator like that at home. There's a really good website called Desmos.com. And if you go there, you can just type the equation, you just punch y equals and actually type it in like it looks. It makes a really nice graph that you can zoom in and out on. And the nice thing about Desmos, you don't have to use all those calculator buttons. You can just start clicking right here and it'll tell you where the maximums are, where the minimums are, and stuff like that. You can find your x-intercepts. So it's a really actually intuitive and easy to use program that you may consider when you're graphing on your own. So it's kind of nice. So anyway, you get yourself a nice picture, and that's how I want you guys to graph polynomials when you have a complicated looking equation. So let's go ahead and look at how you solve the same equation that we just got done graphing a minute ago. Now, we just spent the last couple of videos learning how you factor polynomials, and I showed you 4 methods that sometimes work, but a lot of times don't. This equation won't factor using any of those methods that I taught you guys. But we already learned that really important fact. I made you guys write it down already once in this lesson. And that is that the x-intercepts are the solutions. That's a really big deal because if you know where a graph hits the x-axis, you know the answers to the problem. And if you look, we already took the time to graph this guy. This graph has an answer right here and also right here because we took that equation with a y equals and we plugged in a 0 for y, which is the x-intercepts. So what this tells me is the x-intercepts, or the roots that I already found, are the answers to this problem. So I know the answers for this graph, for this equation, are about negative 1.49 and x equals 3.58. Those are solutions to this equation. Now, I'm going to pause for a second right here, and I want you guys to think. I am going to ask you a question, and hopefully you can already kind of think about where I'm going to be going with this and what my question is going to be, okay? So what is odd or weird or strange about the problem that I just solved? Now, what I'm looking for here, hopefully you had a chance to pause and think this through. This problem is x to the fourth power. But I'm sitting here with two answers to a fourth power problem. So the question is, where are those other answers? Where could they be? What could be going on? So think in your head again about what could be true about those other two answers. Okay? I'm going to walk you through what kids will tell me in class when I ask them that, but I want you to take a second to think about it yourself. One thing I will have kids tell me is, well, maybe the answers are just off the picture. Maybe they're like over here or over here on the far sides of the graph. But remember that polynomials go upwards, the arrows point up or down, and I guess they could happen off the picture, but if I show you my graph right here, my nice picture on the Desmos program here, you can zoom out on this and see that's not going to happen. It's not wrapping back around and coming back down. So if that option is out, what else could it be? There are actually two possibilities for what could be going on. Option one is that my other answers are imaginary. Because if I had an imaginary answer, I would not see it on this picture. And then option two is that my answers right here actually repeat or have a multiplicity of more than one. Those are the two kind of explanations for why I don't see four answers like I'm supposed to. And I have a quick little demonstration here that's going to show you guys how you can identify which situation it is. So on this paper here, I want you guys to go ahead and sketch these three pictures. Just doesn't have to be anything fancy, but I'm going to show you what my equations say, and I want you to write down just a quick thing for what's going on in my picture. I don't think it's going to let me write on these, which is unfortunate. All right, so let me figure out, I think I lost my picture. Here it is. All right, so when I look at this picture, this first graph says negative, and then it's x plus 3, x minus 1, x minus 3. So each of these little parentheses right here only happens one time. And when you look at your graph, it's x plus 3, so I hit it negative 3, x minus 1, I hit it positive 1, negative 3, positive 3, just like you would expect. The graph, what it does when an answer only happens once, is the graph just kind of crosses right through, slices through at negative 3, slices through at positive 1, slices through at positive 3. So each answer, it only hits one time right there. That's kind of what's going on. I think what I'm actually going to do is I'm going to pause this video and I'm going to make these pictures. I'm going to make it so I can actually write on this because I think that will be helpful here. So give me just a minute and I will come back with a better picture here. All right, so now I should be able to actually write on these things, which I think will be easier to understand. As I was saying, if you look at the answers on this first picture here, this would be the answer, x equals negative 3. That's going to be a solution to this parenthesis. We have x equals 1, and we have x equals positive 3. And it should be no surprise to you guys by now that that's where it hits on the x-axis. Now, if you look at what the graph does, each time we have an x-intercept here, the graph just intersects and passes right through that x-intercept. It kind of slices through each x-intercept. That's kind of what's supposed to happen on a normal looking picture here. So make sure you have this equation written down and just sketch a picture like this that hits at those x-intercepts and just goes through like that. You don't have to worry about the tick marks on the y or anything, but get a good picture. Like if I was going to do this one, I'd have negative 3, I'd have positive 1, I'd have positive 3. What I'm looking for on this picture in your notes is just getting at least this part of the picture taken care of. Okay? Then we're going to progress to this guy over here. On this graph, I have the answer x equals negative 2, and I have x equals positive 1. But this x equals negative 2 actually repeats twice because it has a squared on it. So this answer right here is going to repeat. The picture hits at negative 2 and at positive 1, just like you guys would expect. And the positive 1, the one that doesn't repeat, just slices right through like all of the x-intercepts did on this picture. But the answer that repeats right here, the negative 2, it doesn't slice through like the other x-intercepts. What it actually does is it bounces and does not cross over the x-axis to the other side right here. So the root that repeats bounces or makes like a little mini parabola with a vertex on the axis. If you have an answer that repeats an even number of times, you'll see this happen. So if a root repeats like 4 times, you might see something like this where it comes back the same way. Okay? Then I've got one more picture here. And on this next picture, I have x equals 8 and I have x equals 5. The 8 doesn't repeat. So there's 8. You can see it slices right through and crosses over to the other side. And then I've got the answer of 5 that repeats 3 times. So if something repeats an odd amount of times, it does cross over to the other side. But it does like a weird little swervy deal like this right here. It doesn't go straight through like over here. It kind of does a weird move right here. It's called an inflection point, the actual mathematical term for it. But something weird happens at that x-intercept. So if a root is going to repeat in general, you're going to see some sort of disturbance or weird thing going on your picture. All right. So when I look up at this example right here, I would ask you guys a few minutes ago, are the other answers imaginary or do they repeat? Well, both of these answers right here just kind of slice right through those x-intercepts and cross to the other side. What that tells me is that these don't repeat. And actually, the other 2 answers must be imaginary. So that's kind of how I would figure that out. I would look and see if they repeat, and if they don't, then I know I've got an imaginary solution. I'm going to do one more quick thing in this video, and I'm going to break this up into 2 pieces. So I'll have a second video for this section. Let's say I had a picture. And my picture for my graph, really awesome looking picture, I know, right? Looks like this. So I've got this going on. And I want to know what degree could this be? So what degree could this graph be? Well, if I look at this picture right here, you could use the rule with the bumps and that would be all right, but I can also look at my x-intercepts. I have an answer right here that happens 1 time. This answer, where it hits on the x-axis, happens 2 times. This answer happens once, and this answer happens once. This answer I knew happened twice because it bounced back at the x-intercept right here. So if you count these up, 1, 2, 3, 4, 5, I have 5 answers in this problem right here. So I can know there are at least 5 solutions, and there could potentially be extra imaginary solutions on top of that. So that's how you connect the x-intercepts of a graph to the solutions that it's going to have.